Hello everyone, I am your 214 lab TA Nuanjula Samarasinghe. Our next lab is lab number 4, Gauss's Law. So I'm going to give you a brief introduction about Gauss's Law, and I hope this will help for your preparation quiz. So before I move to the Gauss's Law, let's talk about electric field and flux. So actually electric field and flux was your last lab, your third lab. But let's try to understand electric field and flux first, and then I will move to the Gauss's law. What is the electric flux? The electric flux is the rate of flow of the electric field through a given area. So you can write electric flux as a dot product between electric field vector and the area vector. So what is this dot product? So if you remember, we talked about vector algebra in our first lab. We talked about vector addition, vector subtraction, and also vector multiplication. So under the vector multiplication, we talked about scalar product or dot product and a vector product or cross product. So what we have here we have a scalar product or dot product. So that means you multiply two vectors and then the resultant quantity is a scalar. So that's the meaning of a scalar product. So as you can see here, you multiply electric field vector with the area vector and then you will get a flux, and flux is a scalar. So that's why it's called a scalar product or dot product. So now, and then what you can do, you can rewrite this equation as like this. So E dot A is equal to magnitude of electric field times magnitude of area vector times cosine theta. And then what is this theta? Theta is the angle between electric field and the area vector. So then let's talk about three different cases. So case A, the surface is face onto electric field. So that means here you can see, here we have a uniform electric field because you can see field lines are parallel to each other. So here we have a uniform electric field and the magnitude of that uniform electric field is equal to capital E. And then here is our surface. So now you can see the surface, the area vector. Now here it's the area vector. So you can see the angle between electric field and the area vector is equal to 0 because they are going into the same direction. So the angle between electric field vector and the area vector is equal to 0. So therefore, how you can find the flux? Flux is equal to E times A times cosine 0. And we know cosine 0 is equal to 1. So therefore, in this case, you will get maximum flux, which is equal to E times A. So that is the first case. The second case is surface is tilted from a face-on orientation by an angle phi. So now what happened? In this case, you can see the angle between electric field vector and area vector is equal to phi. So then you can find flux. Flux is equal to E times A times cosine phi. Phi is the angle between electric field and the area vector. And then the third case is surface is edge onto electric field. So now what happened? You can see electric field and the surface of they are parallel to each other. So that means the angle between electric field and the area vector is equal to 90 degrees. So when angle is equal to 90 degrees, then you can find flux. Flux is equal to E times A times cosine 90. And we know cosine 90 is equal to 0. Therefore, here the flux is equal to 0. And you can see it very clearly because flux mean number of, and here you can see because electric field lines are not going through the surface. So therefore, you can simply say the flux is equal to 0. The thing I want to explain here is you can categorize flux into three classes: the positive flux, negative flux, and zero flux. And how we can do that? So let's look at this equation again. The flux is equal to magnitude of E magnitude of A times cosine theta. So here's the magnitude. It's just a value, positive value, and here it's also a positive value, the magnitude of the area vector. So that means according to this angle theta, we can categorize flux into three classes. If this angle theta or phi satisfy this condition, then we will have a positive flux. If the angle satisfies this condition, if the angle is greater than 90 degrees, less than or equal to 180 degrees, then we have a negative flux. If the angle is equal to 90 degrees, then we have a zero flux. So we already discussed these things. So now let's talk about electric flux and enclosed charge. So now what you can see here, if you have a positive charge, then we say we have an outward flux. If you have a negative charge, then there is an inward flux. So what is the meaning of that? So let me give you an example. You know, the example always help us to understand a lot of things. So here what you have a positive charge inside this box, and then you know if you have a positive point charge, electric field lines are going away from the charge, so that's why we have an outward flux. And here's the same thing. I changed the magnitude. Now we have two positive charges inside this box, but still they are positive, so electric field lines are going away. But here now we have more flux because more charge means more flux. So therefore, but still here we have outward flux. And here now we have changed the sign of this charge. Now we have a negative charge, negative Q. And then what happened, you know that if you have a negative point charge, electric field lines are coming in. So therefore here we have an inward flux. So here it's the same thing. Now we double the charge and then still we have an inward flux. So that's the meaning of inward and outward flux. So then let's talk about the fifth example. So here what you have just a box and then no charge inside this box. No charge means no electric field. No electric field means flux is equal to 0. And then in this example, this is very important. Now what we have a box, and inside this box we have a positive Q and negative Q. So therefore what happened, due to this positive Q we have outward flux, and due to this negative Q we have inward flux. Then what happened, this outward flux will cancel with this inward flux, and then the net flux becomes 0. But this is very important. The zero charge does not mean zero flux, but no net flux. So because you can see here the net charge is equal to 0. Net charge means plus Q plus minus Q. So then they will cancel and the net charge is equal to 0. But the net charge 0, but it does not mean zero flux, because here you can see we have outward flux and we have inward flux. So zero charge does not mean zero flux, but no net flux, because net flux is equal to 0 because inward flux cancel with outward flux. So that is very important. And the last example is, now what you can see here you have a box, and then behind this box there is an uniformly charged sheet. So then what happened, it's positively charged sheet, and then you can see here the electric fields coming in. So that means you have inward flux and also you have outward flux. So then what happened, inward flux cancels outward flux, then no net flux. So the net flux is equal to 0 here as well. And then this is my last example under electric field and flux. So now what you have here, it's the same thing. You have a box, and inside this box there is a positive point charge. So then what happened, if you have a positive point charge, so we already discussed this one, you have outward flux, right? Okay, so now what happened, now I double this charge. So here you have plus Q, now you have plus 2Q. I didn't change the shape or size of the box. It's the same box, but I changed the magnitude of that charge. Now it's 2 times bigger than the previous case, than part A. So then what happened? If you have a more charge, then doubling the enclosed charge also double the magnitude of the electric field on the surface. So the electric flux to the surface is twice as great as in part A. So that means doubling the enclosed charge double the flux, because if you increase the charge, then electric field will increase, and so that means basically doubling the enclosed charge double the flux. But now what I did, so now you can see, now I have this plus Q again, same as part A, but I changed the dimension of this box. Now the box is twice bigger as the part A. So now the same positive point charge plus Q, but enclosed by a box with twice the dimension. So then the question is, what happened to the flux? So we know flux is equal to dot product between electric field vector and the area vector. So the magnitude of the electric field on the surface is 1/4 as great as in part A. So now by doing this one, we change the dimension of the box. Now it's twice than the part A. So then what happened to the electric field? Electric field decreased by factor of 4. But the area through which the field flows is 4 times greater. But area is increased by factor of 4. So that means here in the denominator we have 4 and in the numerator we have another 4, and then that 4, the 4 in the denominator cancel with 4 in the numerator, and then we will get the same flux, E times A. So that means doubling the box dimensions does not change the flux. That is very important. So here, from here to here, we have the same flux from A and C. The flux in case A equal to flux in case C. So now it's time to discuss Gauss's law. But before I move to the Gauss's law, let me summarize electric field and flux. So we talked about inward and outward flux. The direction of flux depends on sign of enclosed charge. So that means if you have a positive charge, then we have outward flux. If you have a negative charge, then you have an inward flux. And then the second point is charges outside the surface do not give a net electric flux to a surface by symmetry. So that means, for example, we already discussed an example, but here you can see another example. So here it's our surface, and then here we have a point charge, positive point charge, and you can see electric field lines are going like this. But the flux, the net flux through this surface is equal to 0 because this inward flux cancel with this outward flux. And then the last point is net electric flux is directly proportional to the net charge enclosed, but independent of the size and shape of enclosed charge. So that's the last example. So now let's move to the Gauss's law. So now it's time to talk about the Gauss's law. So before I go to the Gauss's law, so let's talk about Gaussian surface. It is very important. So the Gaussian surface, a Gaussian surface, sometimes abbreviated as G dot S, is a closed surface in three-dimensional space through which the flux of a vector field is calculated. So that is the Gaussian surface. And the main thing is these Gaussian surfaces are imaginary surfaces. Okay. And then let me give you some example of Gaussian surfaces. So if you have a positive point charge, then the Gaussian surface around the positive point charge, here you can see it's a spherical, we have a spherical Gaussian surface. And if you have negative point charge, it's the same thing. Again, we have a spherical Gaussian surface. And then here it says we have a positive outward flux. So now we can understand what is the meaning of outward flux. It's outward because it's going away from this Gaussian surface. And why it says positive? So I will explain this one later. So now let's try to understand what's here. So here we have a spherical Gaussian surface and the flux is outward. And here we have a spherical Gaussian surface and the flux is inward. And then the third example is how you can define a Gaussian surface for infinitely long charge wire. So here you can see you have a cylindrical Gaussian surface, and the last example is the Gaussian surface for an infinite plane sheet of charge. So here it's the same thing as part C. So here you can see we have a cylindrical Gaussian surface. So those are some examples for Gaussian surfaces. And then the other important thing I want to tell you is this one. So here it says positive outward flux and here it says negative outward flux. And if you remember, we talked about positive flux, negative flux and zero flux. We categorize flux into three classes according to the angle between electric field and the area vector. So here what happened? So you can, if you have a surface, you can define area vector. The thing is the area vector should be perpendicular to that surface. And then in this case, the important thing is the area vector is chosen by convention to point out of the Gaussian surface. So that's why you can see here is our area vector. So you can see it's point out of the Gaussian surface. So now, for example, if you check here in the first example, if you checked in here, you can see the electric field the angle between electric field and the area vector satisfy first condition. So that's why it says we have a positive flux. And in this case, again, the area vector point out of the Gaussian surface and the electric field lines are going opposite to the area vector, because if you have a negative point charge, field lines are coming towards that charge. And then here you can see the angle between electric field and the area vector satisfy the second condition. So that means we have a negative flux. Okay, so now what we can understand what is the meaning of positive outward flux and what is the meaning of negative inward flux. So let's go to the Gauss's law. So actually uh, this law was first formulated by Joseph Louis Lagrange in 1773, followed by Carl Friedrich Gauss in 1813. So the Gauss's law says the Gauss's law is the total of the electric flux out of a closed surface is equal to the charge enclosed divided by the permittivity. So that means you can define flux as this: flux is equal to Q enclosed divided by epsilon 0. Epsilon 0 is the vacuum permittivity and it's a constant value. So now let's talk about the same example. So we already discussed this example on the electric field and flux. So we checked the net flux. So now let's try to do the same thing. Let's try to find the net flux using the Gauss's law. So in this case, you can see here we have a box, but inside we don't have any charge. So Q enclosed is equal to 0. So that means the net flux is equal to 0. Now it's very easy. And in this case, what is Q enclosed? So I'm trying to find the net flux using the Gauss's law. So here, what is Q enclosed? Q enclosed is equal to 0, because Q enclosed means plus Q plus minus Q. So then they will cancel, and then Q enclosed in this case is equal to 0. Q enclosed is equal to 0 means net flux is equal to 0. And here it's the same thing. So we don't have any charge inside this box. So Q enclosed is equal to 0. Therefore, net flux is equal to 0. And then the last example, here you have a box. Inside this box there is some charge. So here the flux is equal to Q divided by epsilon 0, because Q enclosed is equal to Q. So therefore, flux is equal to Q divided by epsilon 0. And in case B, now Q enclosed is equal to 2Q. So then the flux is equal to 2Q divided by epsilon 0. Now you can clearly see that the behavior of flux from here to here. So it changed by factor of 2. Here it's Q divided by epsilon 0. Here it is 2Q divided by epsilon 0. So we already discussed these things, but here I'm trying to explain you all the things using the Gauss law, because it's very easy then. And then here I changed the dimension of the box, but still you can find the flux using the Gauss's law. So the flux is equal to Q divided by epsilon 0. And if you compare A with C, you can see it's same flux. So even if you change the dimension, flux will not change, because here you have a same enclosed charge, which is equal to plus Q. So flux in case C is same as flux in case A. So here's some example. So the only thing you need to check is what is Q enclosed. And then you can simply apply the Gauss's law, and then you can find the net flux. Now, as a last step, let's talk about one application of Gauss's law. That is very important. So there are so many applications of Gauss's law, but here I'm trying to explain just one application because we don't have enough time. I don't want to spend too much time for this video, but so the example I want to tell you is finding the electric field near a large sheet of charge. So what you have here, so here you have a large sheet of charge, and I'm trying to find the electric field due to this electric field near a large sheet of charge. So here I can define the Gauss's law. If you remember, we already discussed the Gaussian surface for a large sheet of charge. It's a cylindrical Gaussian surface. And then here we can define three areas. So here it's the first area, the side area, and here's the second area, and this is the third area. The side one is the third area. So then those are the three areas for Gaussian surface. So now let's assume the charge density of this large sheet is equal to sigma 0. So the charge density means charge Q enclosed, the charge divided by area. So charge density is Q enclosed divided by A. So then we can solve this equation for Q enclosed. So I'm trying to find the enclosed charge. Now Q enclosed is equal to sigma 0 times A. So you can see that. It's very easy. So now let's try to find the net electric flux passing through this Gaussian surface. So net electric flux, you know, we have like two equations. You can use the dot product between E and A. It's also flux, or you can use the Gauss law. So let's use this one first. The flux is equal to E times AE dot A. So now what happened, as I explained to you before, here we have three areas, A1, A2 and A3. So therefore you have to take all these three surfaces. So let's work on the first surface. So here E dot A, so that means E dot A1. So dot mean cosine. So here you can see the angle between these two is equal to 0. Therefore we will get E times A times cosine 0. Cosine 0 is 1. So that means we will get 1 E times A here. And using the second surface, it's also same as first surface, because you can see the angle between E and A2 is equal to 0. And then again we will get E times A for this surface. So that means here we have 1 E times A, here we have another E times A. Then we need to add these two to find the net flux. So then you will get 2 times E times A, 2EA. But then the question is what happened to the third surface, because we defined third area as well. So in this case, you can see the angle between electric field and the area vector is equal to 90 degrees. So then if you take this product, the dot product, we will get E times A times cosine 90. So cosine 90 is equal to 0. Therefore, there is no contribution. There is no contribution from third area. So therefore, we only have this part and this part. So that's why we only have 2 times E times A. Okay. So then that is the flux. So we found the flux using this equation. And also using the Gauss law, we can find flux, because according to the Gauss law, the electric flux is equal to Q enclosed divided by permittivity epsilon 0. And we already found Q enclosed, which is equal to sigma 0 times A divided by epsilon 0. So that means you found flux using the Gauss law, which is equal to sigma 0 A divided by epsilon 0. And also you found flux using this equation, which is equal to 2 times E times A. So therefore what you can do, you can simply equal these two sides. So sigma 0 A times A divided by epsilon 0 is equal to 2 times E times A. And then you can solve this equation for the electric field. Now you can see the electric field is equal to sigma 0 divided by 2 epsilon 0. So again, sigma 0 is the charge density of this large sheet, and epsilon 0 is the permittivity. So here you can see electric field, the electric field near a charge sheet of large sheet of charge is equal to sigma 0 divided by 2 epsilon 0. So here to get this electric field, we use Gauss's law. So here's one application of Gauss's law. And then I hope you understood. So I hope this will help for your preparation quiz. And thank you so much for your attention, and see you next week. Thank you.